Hello everybody, welcome back to another video. So today we're going to take a look at chapter 6, the short truth table method. As I mentioned in previous videos, this is really a kind of shortcut technique for using a truth table to check whether or not a deductive argument is formally valid or invalid. To be able to use this technique successfully, you really have to have a pretty good sense of what we're trying to do in the long truth table. Because really, in the long truth table, we construct the whole table. It shows us really all the possible truth combinations in the argument, going from the simple statements up to the complex statements. So we see all the possible combinations, and then we just find the rows where the conclusion is false. And really, we're just trying to find the row where the conclusion is false and all the premises are true. Because if we can find one row like that, we know that the argument is invalid. If we can't find a row like that, then the argument is valid. In the short truth table method, what we're going to do is just try to make the row we were looking for in the long one. So there's a handful of steps to this method, and then so today we're just going to walk through what those steps are. So really section 6.1, and then work through some examples, and then on Wednesday, and then probably again on Friday, I'll post some videos just going through examples of how to do this, maybe a few more examples of the long truth table as well. Just to show how this works in practice. So let's start with, well, I now realize that my picture is covering up some of the title. I might have to move that around again. So what are the steps? Well, oh, come on. All right, I'll stick myself down here. Hopefully that's out of the way. So there's really 4 steps to using the short truth table method. We'll just look at what those 4 steps are right here in a summary format. And then in the next few slides, I'm going to take a look at steps 2, 3, and 4 a little bit more carefully because there's some details worth keeping in mind. So the first step for using this method is really just to make a header row for the truth table as we would normally. So when we have an argument, and I've got some examples we'll work through, we make the header row as we normally would. So a separate column for each simple statement, and for each complex statement in the argument, we identify the premises and the conclusion up in that row, and then we just add a single row under that. So instead of, the first difference in making a short truth table instead of a long one, when we do the long one, you make the header row, you put all the information in there, and then you figure out how many rows you make based on 2 to the n, based on how many simple statements you have. When you're doing a short table, you just start with one more row, just one. So instead of adding 2, 4, 8, 16, 32, 64, 128 rows or more, you just start with one. Then what do? Well, you set the conclusion to false in that row. So like I said, we're just trying to construct the row where the conclusion is false and all the premises are true. So we make our header row, we just make one row, we set the conclusion to false in that row, then we try to set the premises to true. Ultimately, what we're trying to do is set all the premises to true while the conclusion is false without contradicting ourselves. That's really all we're trying to do in the short method. If we start with that first row, we make the conclusion false, but we can't make all the premises true, we try again if there is the possibility that there's really more than one possible row, there's more than one way for the conclusion to be false. This is really it. Now, here again, this is pretty simple to sum up in this kind of format. To actually have a good sense of how to do it in practice is a little bit different, but it's good to start with this high-level overview. So what are we doing? Start with the header row, make one row under it, set that conclusion to false, try to make all the premises true without contradicting yourself. And if you can't do that, if you wind up with, in that first row, you just can't make all the premises true while the conclusion's false, then if the conclusion allows for more than one way it can be false, we start making more rows until we either find, or construct really, a row that shows us invalidity, or there just aren't any more possible ways for the conclusion to be false. So I'll say more about that in a moment. Okay, so precisely on this point of setting the conclusion to false. When we have an argument, if the conclusion of the argument is a simple statement, then we just set it to false and you only have to make one row. Because there's only one way for an argument with a simple statement to be, for that conclusion to be false, right? The simple statement is, I don't know, just say it's P. right? If the conclusion of the argument is P, whatever that statement means, for the conclusion to be false, it just means P is false. There just aren't any other ways of doing it. Right? So if that's what there is, you really only have to make one row. Now, if the conclusion is a complex statement, make it false. Fill in the truth values of any logical units included in the conclusion. So if it's a complex statement, right, if it's a disjunction or a conjunction or a biconditional or an implication or anything like that, you're going to make the conclusion false. You then fill in the truth values for the logical units that make up that statement, right? So if it was just a conjunction, right, it was P and Q was the conclusion. You'd make the conclusion P and Q false. You would then make P and or Q false because that's what's required when that conjunction is false. Here again, we'll see what this looks like in practice. If there's more than one way for the conclusion to be false, start by arbitrarily making it false in one of the ways possible and fill in the truth values for any logical units included in the conclusion, right? Just like in the previous point. If you've got a complex statement, you've got to fill in the truth values that go all the way down to the simple statements that make it up. And this is why the short method is a more advanced method than the long method. In the long method, we start with the truth or falsity of the simple statements, work our way up to whether or not the complex statements are true or false. In the short method, we're working backwards, so to speak, or at least we can be, because sometimes we're just dealing with a complex statement first, and we're making it false or maybe true, depending on if it's a conclusion or a premise, and we then have to be able to know what that means for the simple statements involved. Okay, so when we're setting the conclusion to false, if it's a simple statement, that's really easy. You just make the simple statement false. You only have to make one row. And in that one row, you've got a false conclusion. You're just trying to make all the premises true. If the conclusion is a complex statement, make it false in at least one of the ways it can be false. And that means setting some other truth values. So you have to set the truth value of the conclusion to be false. You then have to look at the simple statements that feed into that complex statement and possibly other complex statements as well, and make those values correspond to the falsity of the conclusion. We'll see what that means in some of the examples we work through. Now, set the premises to true. What are we really trying to do here? Like I said, ultimately what we're trying to do is construct a row where the conclusion is false and all the premises are true. So our goal here is to try to make the conclusion false while all those premises are true. Now there's a sequence that I set out in the primer, and if you follow the sequence, you should always work through it in some sense the most efficient way possible. I'll try to follow those steps as I'm working through the tables I'm looking at. Strictly speaking, you don't really have to follow these steps. Now, certainly the first step is a good one. So when you're trying to set all the premises to true, and remember, it's premises we're trying to set to true. It's not just all the statements. It's just all the premises we care about. Start with all premises that are simple statements. That one I will stress. Start with the simple statements. Whenever you have premises that are just simple statements, all of the premises have to be true while the conclusion is false to show us invalidity. So if you just start with premises that are simple statements, those are very easy to set. That helps give you extra information you can use when you're taking a look at other premises. This is a very good place to start. So just start with all the simple statements. Next, making all the premises that are negated simple statements true is a very easy next step. Because there again, if you've got a negated simple statement, just by saying it's true, you know the simple statement's false, and then you can use that information knowing that the simple statement's false whenever you're then looking at a complex statement that involves the simple statement as well. Setting all conjunctions that are premises to true as the next step is also very handy. Why? Because when a conjunction is true, both of the conjuncts is true. So by setting a conjunction to true, you also automatically then know that you've got two other statements, both of the conjuncts, that are going to be true as well. Next, if you set all of the premises that are negated inclusive disjunctions, so negated injunctions and negated implications, if you make those true, negated disjunctions, negated implications. Those are also very helpful to engage with as a next step, precisely because those also only have one set of truth conditions. So remember, disjunction is only true, or a disjunction is only false when both disjuncts are false. Which means if we have a negated disjunction, the negated disjunction is only true when both disjuncts are false. Similarly, an implication statement is only false when the antecedent is true and the consequent is false, which means a negated implication statement is only true when the antecedent is true and the consequent is false. Now, this might have suddenly been complicated, right? What's the real upshot here? By going in this order, what we're trying to do is deal with premises in an increasing level of complexity. So we're starting with the simplest kind of premise, just a simple statement, and then we're working our way up to complex statements that have various truth conditions. So a simple statement is only true if it's true. A negated simple statement is only true when the simple statement is false. Whenever a conjunction is true, both of the conjuncts are true. Whenever a negated disjunction or a negated implication are true, we know something about both of the logical units involved. We can say for sure that two other things are false, or one thing is true and one thing is false when it's an implication. Lastly, after we've gone through these, we just try to set the truth values of all the remaining premises to true without contradicting ourselves. That's really the key. We're just trying to make, I don't know where to put my little video thing. We're just trying to make all the premises true while the conclusion is false without contradicting ourselves. That is ultimately the aim. If you keep just that in mind and you understand how all the various operators work, how the different complex statements can be true or false, then you can use this method. Okay, on to that fourth point. If you don't succeed, try again. Now, there are limits to doing this. All right, I still don't know where to put myself here. If there's more than one way for the conclusion to be false, repeat this process of constructing a row, making the conclusion false, trying to make all the premises true. Repeat that process until either of these conditions are met. One, you construct a row that shows invalidity. That is, you successfully make all the premises true while the conclusion is false, and you never contradict yourself. That is, you never have to say any statement is both true and false at the same time in the same row. So you can stop once you've constructed a row that shows invalidity. All the premises are true while the conclusion is false. Or, two, you construct enough rows to exhaust all possible ways that the conclusion can be false without finding an instance of invalidity. So when we're looking at an argument, and we look at the conclusion, when you look at the conclusion, really the number of ways it can be false, in terms of simple statements that make it up, tells you the maximum number of rows you'll have to construct. This is why if we only have one simple statement as the conclusion, all we have is one row, because there's only one way for that conclusion to be false. The simple statement's false. That's it, the end. If you have something else, a statement that could be false in different ways, say a conjunction, right? A conjunction is false when either or both of the conjuncts is false. So if the conclusion is a conjunction, right, P and Q say, that conclusion is false. We always have to set it to false, but it can be false when P is false or Q is false or both P or Q is false. So there's three ways that conclusion can be false when we're thinking in terms of the statements that make it up, right? P is true and Q is false. Q is true, but P is false. Both P and Q are false. In all of those situations, P and Q is false. So if P and Q is our conclusion, we have a maximum of 3 rows that we might have to construct, because there are 3 possible ways for that conclusion to be false based on the logical units that make it up. Something important to keep in mind, and this cuts through everything, all the various steps, all the different tips. Whenever you have enough information to fill in a truth value, do so. What does that mean? Well, when we're filling in the truth values for a complex statement, a conjunction or a disjunction or whatever it might be, if we have enough information to go and fill in some other truth value on our table in the row we're constructing, then we should do it. Now, we are going to try to avoid arbitrarily setting truth values as much as possible. But sometimes we just have to do that. If we have a conclusion we're trying to make false, and it can be false under different conditions, right? Say that a conjunction, P and Q, it can be false in 3 different ways. Well, if that's the conclusion and that's where we start, then we just have to pick a way to make it false. We have to be arbitrary in some sense. What we're trying to do is go from the most specific information we have to more general claims. So we start with our simplest statements, and then we get into more and more complex statements as much as we can, in the hopes that the information we already have on the table is going to help us fill in the rest of the information we can. Okay, and so look, let's just take a look at some examples now. I think that's really the best way for us to get a good sense on exactly what is going on with these different rules. So we're going to start with some pretty simple short truth tables. We'll just start here. Like I said, we're going to go on and we'll make some more of these in the next video. So I'll work through some more examples next time, some more complex examples as well. So we're not going to see a lot of dealing with really difficult conclusions today, but we'll get into that next time. So look, very simple argument again, and you should already know, just based on what we've been doing in the past, this is a valid argument. Premise 1, if P then Q. Premise 2, P. Conclusion, Q. This is just a straightforward affirming the antecedent, right? We've got an implication statement as a premise. We've got the antecedent. We've got the consequent as the conclusion. So it's a valid argument. I can just say that right now. But we're still going to make the table to see exactly how this works. So look, what do we need on our table? Well, we have to start by making a normal header row. That's really what we're going to start with. So what we were doing in the long truth table still applies here. We've got 2 simple statements. We've got P and Q, so we need columns for that. We also have 1 complex statement. So what do we need? We only actually need 3, well, that's not where that should be. We only need 3 columns. Right? We need P, we need Q, and we need if P then Q. Right. Do all that. Make this bold. Give it a little shading, just to make it look nice. Okay, so we've got all this, and then we have to remember to label our premises and our conclusion. Now, so far we've just been doing what we would do with a long truth table. This is where the first difference comes in. If this was a long truth table, we would be adding 4 rows because we have 2 simple statements, P and Q. Because we're only using the short truth table method, we only add 1 row. Right? That's all we're doing now. We're just trying to make the row we need to find. So let's try to do it. So what do we do? Well, remember, and it could be helpful in going through this part of the video, just to have up those rules from the formal logic primer. So we've done the first step. We've made a header row, right, with all of the parts it should have. We've made the first row. So now we set the conclusion to false. Right? So the conclusion's false. That's what we're trying to find. So our conclusion is false. Okay, good. Now what do we have to do? Well, because this was a simple statement, you know, the conclusion's just Q, it's false, and then that doesn't give us any information we can fill in anything else on the table with. So now we're just going to try to start making the premises true. Now, in the order that we had laid out, the first thing we look for is to see if we have any simple statements that act as premises. We do. Premise 2 is a simple statement. Premise 2 is just P. And so we can make that true without worrying about it, right? We just know P is true. We need all our premises to be true if we can. So we say, okay, P is true, and that doesn't contradict anything else we know. All we knew so far is that Q was false. P being true doesn't contradict the fact that P is false, right? We would be contradicting ourselves if we had to somewhere else say that Q was false, but we don't here. So look at that. We've got 1 premise set to true, the conclusion is set to false. We only have 1 value left here, 1 cell value. We know we only get 1 shot. at this, we only have to make one row because there's only one way for this conclusion to be false. So we're now on to if P then Q, premise 1. Now we want to make that true. I'm going to fill in true here. But let's look at the values we already have on our table. We've got P is set to true and Q is set to false. Think about the truth conditions for an implication statement. An implication statement is always true, really, unless the antecedent, the first thing, is true, while the consequent, the second thing, is false. That's what we see in this row. P is true and Q is false, and when the antecedent is true and the consequent is false, the implication statement is false. So if we fill in true here for the implication statement if P then Q, we are actually contradicting ourselves in this row. Why? Well, just think about, I'll make this really quickly here, just for the purpose of demonstration. So this is not something you ever have to do. I'm only doing this just to show us this. So look, what I'm constructing now is just the truth table, the definitional truth table for the implication statement. All right, we've got true, true, false, false, true, false, true, false. Of course, we should get rid of the premise and conclusion because that's not. This is just the truth table for an implication statement. All right. And look at this row, right? This is the only row where the implication statement is false. And it's false because the antecedent is true while the consequent is false, right? Because the implication statement is just telling us if the antecedent, right, if P is true, then Q has to be true as well. That's the minimal claim it's trying to make. And so that statement's false when P is true but Q is false, because that's really the opposite of what the statement's telling us. So if we go back up to what we're looking at here, right, we filled in true for premise 1, if P then Q. But of course, if we look back to our truth table row, we have the same truth conditions for P. P is true, right? Q is false. What does that tell us? Well, like our definitional truth table shows us, that means if P then Q has to be false as well, right? We can't say if P then Q is true, well, P is true and Q is false, without just contradicting ourselves. So we have to fill in false for premise 1. Right? To say that it's true is to result in a contradiction in that row. So we're forced to say P1 is false. What does that mean? Well, it means this argument is valid. We cannot set all the premises to true without contradicting conclusion is set to false. Right? If we try to set all the premises to true while the conclusion is false, we wind up contradicting ourselves, right? Because when the conclusion is false and premise 2 is true, we can't make premise 1 true without contradicting ourselves. That's really it, right? And then we're done. We don't have to make the rest of the truth table. All we needed was this one row. Okay, let's take a look at another example. All right, so example 2. If P then Q, Q therefore P. Well, this one's going to be relatively straightforward as well. We've got what? We still have P, we still have Q, we still have if P then Q. All that's really changed this time is what is acting as a premise and what's acting as a conclusion. 2. Now P is the conclusion. And again, we're only going to want one row. A little shading again. Now this time we're going to start by making P false, because P is the conclusion. Up above, in our first example, Q is the conclusion, so we started by making that false. So this time we're going to start by making P false. We always start by making the conclusion false. And we know our job is going to be easier if the conclusion is just a simple statement. So now the conclusion's false. Now we try to make all the premises true. Now this time we're going to start by making premise 2, that is Q, true because it's a simple statement. Now we move on to try to make premise 1 true. Can we make premise 1 true this time while premise 2 is true and the conclusion is false? Well, if we take a look at it, what do we think? We actually can. Right? We can do that without contradiction. I'm going to just copy and paste this truth table, the definitional truth table for the implication statement again. What's going on this time? Well, up in the first example, really what we were seeing was this row being constructed, right? The red row. Now, this time, what are we actually looking at? Well, we had the conclusion P was set to false. I'm going to get rid of this shading here. We had P was false, so we know it was one of these two, right? So really, what were we making? We're making one of the rows on this longer truth table. It's just a question of which one. So we started by making P false, so we know it's one of the last two rows. We then made Q true, because that is a premise. And so if we just look at the definitional truth table when I'm filling in here, we actually know at this point we're filling in this row, right? We had P is false, Q was true, and in this row of the truth table, if P then Q can be true as well. And that's exactly what we have up here. Both premises are true. Well, the conclusion is false. Look at that. This argument is invalid. Both premises can be true while the conclusion is false without a contradiction, right? We say P1 and P2 are both true here, and the conclusion is false. If we just look down at our truth table, we see that. We were really just making one of the lines out of the truth table. Now, when you're dealing with a fairly short argument like this one, you've got a long truth table, it's only 4 rows anyways, you're saving yourself a little bit of time, but maybe not too much. You start saving yourself a lot more time when the argument gets more complicated. And we'll see that with some of the other examples below. Okay, let's take a look at another one. So I hope this is starting to make sense, especially if you're looking at the steps. We start by making our header row. We then start with one row. We always set the conclusion to false. And we just try to make all the premises true without ever having a situation where we have to say the same thing as true or false at the same time. So let's take a look at another one. A little bit more complicated, not too much. Right? Now we've got a negation in there. So we've got P or Q, not Q. Conclusion C. Oh, that's a little tricky. So what's going on? And here, maybe instead of C, just for explanatory purposes, let's make the conclusion F. We'll make it F, just so it's not a C. Okay, how many columns do we need? We need our header row. Let's say we have P, Q, F, not Q, and P or Q. We need 5 columns in our header row. We need P, Q, F, not Q, P or Q. And we need to label our premises and our conclusion. And you probably know just by looking at it that this is not a valid argument. Why? Because the conclusion F doesn't show up in any of the other premises. So there's really no relevance here of the premises to F, but we'll still make it anyways and take a look. So we've got a slightly more complex argument this time. We've got more columns, we've got more letters involved. Now, if this was a long truth table, because we have 3 simple statements, we would need 8 rows. Because this is a short truth table, we only need 1. The conclusion F is false when F is false. So we fill that in. We just say, okay, the conclusion's false. That's always how we start. Conclusion is false. Now let's try to make both premises true. Now, if we look, this time, both premises are complex statements. We have a negated simple statement. We have not Q, and then we have P or Q, right? So we don't start by filling in the simple statements. We always go to the premises after the conclusion. and we have enough information to fill in some other part of our truth table, we do it. So if we go back to the steps set out in number 3, begin setting the premises to true. We start with setting the premises that are simple statements to true. We don't have any premises this time that are simple statements. They're both complex statements. So what do we do next? Well, the second step, after we've tried to set all the premises that are simple statements to true, we then move on to setting premises that are negated simple statements to true. So I have to choose between premise 1 and premise 2 here. Which do we set to true first? Start with premise 2. Why? Because it's a negated simple statement. We know we need the premise to be true, so we can just say P2 is true. This gives us enough information to fill in another cell in our table. If not Q is true, then Q has to be false, right? And so we can just do that on this row. If not Q is true, Q is false. We need to make not Q true because we need premise 2 to be true. That means Q will be false. Great. That gives us a bit more information we can use when we're trying to fill in the truth values of other more complex statements. Now in this argument, we only had one negated simple statement. We set it to true. So now we just move down our list of premises. Now in this case, we only have one other premise, so it doesn't really matter. But if we look, in order of setting premises to true, we should then try to set the truth values of all premises that are conjunctions to true. We don't have a conjunction. Set the truth value of negated disjunctions and negated implications. We don't have those. Then we move on to everything else. And we're just trying to avoid contradicting ourselves. So can P or Q be true in this row without a contradiction? Well, let's look. F is false. That doesn't have any bearing on P or Q, right? Not Q is true, which means Q is false. Okay, so we know Q is false. We've got P or Q. P or Q is true as long as either P or Q is true. Let's try to make it true. So we say this is true. Now to actually know that we haven't contradicted ourselves, we have to go look at the truth values of the simple statements that make up P or Q. So we say P or Q is true, but we know already that Q is false. That means P has to be true. Can we make it true? Sure, we haven't filled it in yet. We can say P is true. Now, do we know P is really true? No. But what we're doing here is trying to test the argument for validity. We're trying to look for a situation where the premises could all be true while the conclusion is false. This row shows us exactly that. The conclusion F is false. Both premises are true, and we can look at the simple statement values that make both of those premises true. So in the situation, in the row, if we had a long table where P is true, Q is false, and F is false, in that situation, we know our conclusion is false. We know that premise 2 is true because Q is false, right, and not Q is true. We also know that premise 1 is true because at least P is true. So this row shows us that this argument is invalid. We could make the whole table with all 8 rows, fill in all that information, and then when we find this row on it, we would know that the argument's invalid. Using this method just is a kind of shortcut. So this argument is invalid. So the conclusion is false while the premises are true, and those premises do not contradict themselves. Right? There we go. Right? And that's really what we're seeing here. Okay, let's just move on to another example. Now this example is a more complicated one. Right? We have P or Q. If Q, then not R. Not P is a premise, therefore not R. Whew. Is that valid or not? Now, I could think about it for a moment, and I could tell you off the top of my head, but it's a lot better to be able to make the truth table and being able to show it. So what do we have here? Well, we need to make our header row. We're going to have more in our header row this time, right? We've got, so just looking at it, what do we have? We have P, Q, and R. So we need 3 columns just for the simple statements. We also have not R. So we need another column, we have not P, and we have P or Q, and we have if Q then not R. We need 7 columns, right? 7 columns here. So what are we going to do? Well, we do what we usually do. We start by filling in our simple statements P, Q, and R. We need a column for not P. We need a column for not R. And again, we should try to move in increasing order of complexity. We need a column for Q, then not R. And we need a column for P or Q. We need to label our premises and our conclusion. We're going to start by making 1 row. Remember, it doesn't matter how complex that argument gets, you start with 1 row. We always start by making the conclusion false. And in this case, we have a negated simple statement. How many ways can that be false? 1, right? What are the simple statement truth conditions for not R to be false? Well, that tells us R is true, right? So just by setting the conclusion to false, we have enough information to fill in another cell in our row. We know not R has to be false because it's the conclusion. That's just what we're trying to do. We're trying to make the conclusion false while the premises are true. So not R is false, and whenever not R is false, R must be true. So we set in that value for R. Now, when I'm talking about contradicting ourselves, really what I'm trying to get at is if we ever fill in a truth value somewhere and we say it's one thing, true or false, if we ever then, in the same row, need it to be the other value, then we've contradicted ourselves. So in this case, if we ever need R to be true, we just can't do that, right? Something's got to give somewhere for the sake of consistency. Okay, so we've got our conclusion false. We've got our 1 row constructed. We're only going to need 1 row because there's only 1 way for that conclusion to be false. So now it's just a matter of trying to fill in all the rest of the cells in this row. Remember, we're focusing on premises, not the simple statements themselves. So we'll go to the premises now. Do we have any premises that are simple statements? No. So let's move on to any premises that are negated simple statements. Those are very easy to deal with. P3 is a negated simple statement. P3 is not P. Now we want that to be true because it's a premise. So if not P is true, then P must be false, right? Just by saying that premise 3 is true, we're saying that not P is true. And whenever not P is true, the complex statement not P, then the simple statement P is false. Just think about the operator table for not P. Whenever not P is true, P is false. If not P is false, then P is true. Okay, so we're done that. Now what do we move on to? Well, we don't have any other negated simple statements, so we'll sort of move down our list. Do we have any conjunctions? We don't have any conjunctions that are premises, so we should move on. Do we have any negated disjunctions or negated implications? No. You might have looked at P2 and said, well, there's an implication statement that has a negation in it. It has not R. That's true, but really what we're talking about in that step is if the whole implication statement itself is negated. So if this was our premise, not if Q then not R, then we would deal with that next. That would be next up on our list, but it's not. So really we're down to 3E, just trying to set all the other premises to true while the conclusion is false without running into a contradiction. Well, let's take a look here. Let's just deal with premise 2 to start with. Right? We've got 2 premises left. It doesn't really matter which order we try to deal with them in. So we'll start with premise 2 here, and then maybe I'll back up and just show how we could go about it dealing with premise 1 first instead. So premise 2, if Q then not R. What information do we already have that's relevant to whether or not this premise can be true? Well, we don't know if Q is true yet, right? We haven't set that value, but we have set not R. Not R is false, right? And so if we think about this on an implication truth table, what do we have here? We have the consequent being false, not R is false, if we say we want P2, right, if Q then not R, this needs to be true. Now, an implication statement is true unless the antecedent is true while the consequent is false. We want our implication statement, premise 2, to be true, so we said that here. We know our consequent is false, not R is false, because that was the conclusion and that's what we started with. What does that tell us? That tells us we have to set the value for Q to be false. Why? Because if the implication statement, if Q then not R, is true, it cannot be the case that Q is true while not R is false. We already know that not R is false, so we can't let Q be true, right? So now we filled in our last simple statement value, right? We know that Q is false along with P and R. We have our conclusion false. We have two premises false. Now we've got one premise left to try to fill in, P1. P or Q. That can be true so long as either P or Q or both P or Q is true. Let's look over to our simple statement columns on our table. Uh-oh, they're both false. So P1 has to be false, right? We have to fill that in. To say P1 is true would be to contradict ourselves, because to assert P or Q is true is to say at least P or Q or both P and Q are true, right? To say P and Q is true is to just say it's not the case that both P and Q are false, which is exactly what we said in this row already. We look over at P and we look at Q, we've said that they're both false. So P or Q must be false. So look at that. If we made all the premises true here, right, if we had said that premise 1 was true, we would have contradicted what we had already said about P and Q. That's why we had to make P or Q false, which means that this argument is valid because we weren't able to make all three premises true while the conclusion was false in this row. Okay, now I said I was going to back up and try to deal with these two premises in the opposite order I dealt with them. So if you remember from just a few moments ago, we were in this situation. The conclusion was false, which told us that R had to be true. We know that premise 3 was true, right, which tells us that P is false. So now instead of dealing with premise 2 and then premise 1, let's deal with premise 1 and then premise 2. So look, premise 1, can we make that true? Yes. We can say premise 1 is true, P or Q. We know that P is false, so we have to say Q is true, right? Because it's only if Q is true while P is false is P or Q true. Now we go and take a look at premise 2 last. Can we make that one true without contradicting ourselves? Not this time. Why? Because if Q then not R is only true, in situations where if Q then not R is false, when Q is true and not R is false, right? When the antecedent is true and the consequent is false. That's exactly what we have here, right? If we had any situation really other than this in terms of the values of Q and not R, we could say the statement is true. But in this row, our antecedent Q is true now, and our consequent, not R, is false. And in that situation, if Q then not R itself is false. So what we have here is a valid argument. The conclusion is false. Oh wait, no. I'm sorry. I'm sort of going on autopilot. It can be a little bit taxing trying to do this in Word and sort of make the video all at the same time. My apologies. So ignore what I just wrote. This argument is valid. We cannot set the conclusion to false while all the premises without contradiction. So this is a valid argument, right? Now, if we had a full truth table, we would have to make a full, 8 rows. And we'd have to fill in all the values and all the columns, right? We'd have to fill in all those cells, so we'd have 8 rows. So what, we'd have 64? No, not 64. 50 some cells we would have to be filling in here. And instead, we've just got this, right? This is all we had to do. That's not too bad. That saves us quite a bit of time if we know what we're doing. Okay, let's take a look at one last example. Now, this time, I've got a complex statement as the conclusion, and it's a negated complex statement. So here again, we need to start with a header row. How many columns do we need? We've got Q and R and P. So we've got 3 simple statements. So we know we're going to need 3 columns. Then we also have Q and R. That's a complex statement, so there's a 4th column. If R, then P, that's a 5th column. We have P or Q. That's going to need a column. We then have the negation of P or Q. That's going to need a column. So we need 7 columns here. So we need Q, we need R, we need P, we need Q and R, we need if R then P, we need P or Q, and finally we need not P or Q. Then we need to label our premises and our conclusion. Okay, so we've got our header row. Now we need to start filling in truth values. As usual, we need to start by making the conclusion false. So the conclusion is false. Our conclusion is a negated complex statement. The conclusion is not P or Q. All right. Because it's a complex statement, we're going to have more truth values to fill in. Knowing that that statement is false, not P or Q, gives us information with which we can fill in other cells in the table. So not P or Q is false. Remember, double negation adds up to an affirmation. So if, or another way to put it, right, when the negation is false, the statement itself should be true. So not P or Q is false. That means P or Q is true, right? If we look at it. So when not P or Q is false, P or Q is true. If we just put this on a simple negation truth table, remember on that truth table, when you've got a statement, its negation is true when the statement is false. If the negation is false, the statement is true. It's just the opposite, right? So in this case, we've got not P or Q being false, so P or Q has to be true, right? So what does that mean? Well, we again have more information here. So P or Q is true. Under what conditions is P or Q true? Well, it's true when P is true or Q is true, or both P and Q are true. Okay, so if we look over to our simple statement columns, we've got Q and P over there. What should we do? Well, we're in a situation now where this conclusion can be false in more than one way. So when I was talking about the different ways the conclusion can be false, in one sense, if we just look at the complex statement, P or Q, there's really only one thing to do here. The conclusion has to be false, so this complex statement, P or Q, has to be true. But the fact that P or Q is true doesn't tell us on its own what the truth values of the simple statements have to be. So there are 3 possible ways this conclusion could be false. Right? And for the sake of demonstration here, I'm just going to fill in all 3 of those rows. Normally you just go 1 row at a time. I'm going to make all 3 rows just to show it. In all 3 rows, we're going to have this situation. The conclusion's always false. Right? In this case, because it's a negated complex statement, the complex statement will be true because the negation's false. So we're always going to know this. But the fact that P or Q is true only tells us that one of 3 situations is the case. Either both P and Q are true, we'll put that in the first one, or one is true while the other one's false. These are our 3 possible situations. These are the 3 possible rows we can construct in the short truth table. This is what just knowing that the conclusion is false tells us that we're dealing with really these 3 rows. So if we had a long truth table with all the information, right, with all the simple statements filled in, all the complex statements, it would be these 3 rows that we find the conclusion to be false. And so those are the only 3 rows that we need to potentially construct. Now in this case, let's just go row by row to see what happens as we keep filling it in. So we've got 2 premises, right? We've got a conjunction, we've got an implication statement. If you think back to our list, what order should we fill these in? Fill the cells in. That still came out awkwardly. What order should we approach these in? There, that sounds a little bit better. Well, look, we don't have any simple statements as premises, so we can't do that. We don't have any negated simple statements. The third thing we look for are conjunctions, right? Q and R. That's what we're going to want to make true next. Why? Because we know when Q and R is true, both Q and R must be true. So by saying this premise is true, we go and look at our columns for Q and R. We already know Q is true. That's good. Then we need to make R true as well. Because if we've said Q and R is true, as we're doing with premise 1 here, then we need to say both Q and R are true in their respective columns. That leaves us with 1 premise left. If R, then P. Can that be true in this row without us contradicting ourselves? Actually, it can. Look at that. R is true and P is already true in this row. And when the antecedent and the consequent are true, their implication statement involving them is true. So this row has already shown us invalidity. Right? If we just take a look at it, we've got the conclusion is false, both premises are true. We can just stop there. On that first row, the conclusion is false, well, both premises are true, and there's no contradiction involved. So this is really all we would have to do to use the short truth table method to figure out whether or not this argument is valid or not. Just for the sake of demonstration purposes, I'm going to fill in the other couple of rows just to see what we get, right? You don't have to do this. When you're actually using the short truth table method, stop as soon as you've constructed a row that shows invalidity. That's one of your, in some sense, success conditions. That's one of the end conditions. Now, let's just fill in the last 2 rows just for the sake of seeing how this works a little bit more. So we always know the conclusion's false. So that's not P or Q. Given that the conclusion's false, we know P or Q is true. In the second row, we've just artificially made Q true while P is false, just to see what happens, because P or Q is still true in that situation. So again, we're going to fill in our premises in order, and because P1 is a conjunction, we're going to do that one before we do P2, because P2 is an implication statement. So here again, we would want to make P2 or P1 true, which means we need Q to be true and R to be true. We can do that again in this row, right? And now the statement, if R then P. Well, if we look in row 2, we actually can't set that to true because we've got the antecedent R is true, the consequent P is false. So if we said if R then P, we would just contradict ourselves based on the other information we have in the row. So in this row, we'd have to say that's false. In the last row, same thing, we want to make if Q, or we want to make Q and R true, because that's our first premise. But take a look at what we got. We already know Q is true, or Q is false. Sorry. We already know Q is false. If Q is false, Q and R can't be true. It has to be false, right? We could say that R is true. Nothing makes us say R is false. But because Q is already false, we would have to say Q and R is false, no matter what the value for R is. Now, in this row, if R then P, we can make that true, right? Look, I just said R would be true based on Q and R, but I even didn't have to do that. Because I know Q is true, I know Q and R is true. Do I really need to know what the value of R is to say Q and R is true here? Not really. Because I know Q is false, I know the conjunction that involves Q is false. So let me just leave R open for now. What happens if I go over to if R then P? Now, of course, I've already set one premise to false here. Given that I've got a false premise, I know this row isn't going to do what I want it to show me. Right? I need to be able to have all those premises be false, or all the premises be true while the conclusion is false to show invalidity. If I wanted to try to finish this row off anyways, just filling in the values, could I make if R then P true? Well, I've got no value for R. I can say this is true, right? Why? Well, if I go over to the R column, in this situation, I know premise 1 is false because Q is false, but because I've got a true consequent on if R then P on premise 2, I can say premise 2 is true. It doesn't matter if R was false or if R was true. Premise 1 would still be false and premise 2 would still be true. So in this row, this third row, say we had started with the third row, just arbitrarily. That's what we had set our P and Q values to when we're making the conclusion false. Ultimately, in this row, R could be true or false. So there's two different rows in the long truth table that we're really putting together here. And our premises would still have the same truth values, no matter the truth value of this particular simple statement. So in some sense, this simple statement is kind of a dangler, right? We don't have enough information to say definitively if R is true or false in this row. So we can just sort of keep in mind, it could be either one. Now, for the sake of actually making the table, we pick one just to fill it in. But like I said, given that on our very first attempt, we showed that this argument is invalid because the conclusion is false when both premises are true, really we could just stop right there. Okay, I hope particularly that last example wasn't too confusing. We're going to get into some more examples of this on Wednesday in the next video. Well, basically in that next video, we're just going to explore more examples and just do this more. So read the chapter, look through the examples there, take a look at some of the practice questions. But really for the remainder of this week with the last 2 video lectures that I'm going to put up, I'm just going to work through some more examples using the short truth table technique. And I'll try to do a video where I'm using both the long and short techniques together just so we can see for comparison purposes how the two of them line up with each other, how the short table is really just a version of the long table. And hopefully walking through it in this way will help show how to actually do this, how to not only learn the rules of making a truth table and how to check it, but how to actually work your way through it and see what's going on in there. As I've mentioned before, the Philosophy Help Center is now running virtually on Thursday afternoons. So if you're having difficulties really getting the hang of any of this material, which some people do, right? Don't feel any shame or anything like that, especially with all the truths and falses. In this video in particular, I apologize, especially near the end. I was starting to in some sense, mix myself up in terms of what I was talking about being true or false, or which premise it was, or which piece it was. So it can be very easy to cross wires a little bit, to have a good sense of what's going on, but still, just as you're looking through things, to sort of get a little confused here or there because there's so many truths and falses going on. There's so many different values to fill in and so many different columns and everything. It's quite all right to have a little difficulty and go ask for some help. And the Philosophy Help Center and the tutors there is a very good place to go do that. They can help walk you through any of these issues, talk through anything that's causing you some confusion. And if you've got some work you want to try to do, of course, now we're in this digital environment, so there might be a little bit of a difficulty just trying to, in terms of the technology, in terms of sharing what you're doing, but you can try to work through some problems with them as well, and just sort of go through step by step to see how these things are supposed to work. So I hope this video has been helpful. I hope my slips of the tongue didn't cause too much confusion here. I hope you've got a good sense of at least what is going on in the short truth table method and how we approach it. And next time we'll look at some more complex arguments that we can use the short truth table method to check for validity and invalidity in a much more efficient way than we can use the long truth table to do so. So I hope you're all doing well, and I'll see you again on Wednesday in my next video. Bye for now.